When you type a question and an AI answers you in perfect sentences, what is actually happening underneath? Let's open the black box. Here's the honest first reaction most people have. It feels like magic. Words go in, a thoughtful reply comes out, and in between there's just a box we're told not to worry about. It is not magic. Every single step inside that box is ordinary math. Addition, multiplication, comparing numbers, repeated an almost unimaginable number of times. There is no understanding hiding in there in the way a human understands. Just patterns, learned from data, at a scale that's hard to picture. So today we're going to walk through that box, one honest step at a time, with no step skipped and no hand waving. By the end, you'll be able to trace exactly what happens between you hitting enter and the reply appearing on screen. We'll build this up piece by piece because each idea depends on the one before it. First, tokens. How your text even gets chopped into pieces a model can read in the first place. Then embeddings. How those pieces turn into numbers that somehow capture meaning, not just spelling. Once we have meaning as numbers, we hit the real heart of the whole system. Attention. How a single word figures out which other words in the sentence actually matter to it, and which ones it can safely ignore. Then the transformer, the architecture that takes that idea and stacks it deep enough to be genuinely useful. And finally, the two halves of the model's life training. How it learns from a mountain of data before you ever meet it, and inference, what happens the moment you hit enter, and it starts writing its reply back to you, one single word at a time. We're going to take our time with each one. No idea here is complicated on its own. It's the combination and the sheer scale that makes the end result feel intelligent. By the end, a single sentence going in and a reply coming back out will make complete sense to you, start to finish. Before a model can think about your words, it has to cut them into pieces first. Those pieces are called tokens, and the way it cuts them is stranger than you'd expect. Let's take a real sentence. I love tokenization, and slow everything down so we can watch exactly what happens to it before it ever reaches the model. Your first guess might be, it splits on spaces into words. I love tokenization. 3 whole words. Done. That seems reasonable. That is not what happens. A tokenizer doesn't split on whole words the way we just guessed. It splits on frequently seen chunks of characters, learned in advance from huge amounts of text. Common words like I and love stay whole because they show up constantly. But tokenization, a rarer, longer word, gets cut into 2 familiar pieces. Token and ization. So why on earth would you deliberately break apart a perfectly good word? This is the part worth sitting with, because the answer explains almost everything else in this video. The model only knows a fixed vocabulary, say 50,000 possible tokens decided once ahead of time. But human language can form an effectively infinite number of words. Those 2 facts don't fit together unless you allow words to be built out of smaller, reusable pieces. So here's the actual mechanism. Each chunk is looked up in that fixed vocabulary table and replaced with a number, its token ID. I becomes 40. Love becomes 3021. Token becomes 11,241. Ization becomes 3,325. From this exact point on, the model isn't looking at letters at all anymore. It's looking at a short list of integers. And now that question from earlier answers itself. Watch what happens with an unusual word. Cat is common enough to earn its own single token. But a rare or made-up word like flibbertigibbet has no dedicated slot in the vocabulary, so it gets spelled out piece by piece, using smaller fragments the model does recognize, until the whole word is covered. So step 1, always, no exceptions. Your text becomes a short list of numbers, not letters, not words in the way you think of them. Numbers built from reusable pieces the model was already taught to recognize. But a list of numbers still has a problem. Right now, those numbers carry no meaning at all. 3021 doesn't look close to any other number just because love is a warm word. That gap from numbers to meaning is exactly what we solve next. A token ID is just a number. It has no meaning by itself. So how does the model know that king is closer to queen than it is to banana? Let's find out. Remember where we left off. Every word is now just a token ID, a plain integer. And plain integers are a problem. The number for king and the number for banana are just as close numerically as king and queen are. Numerically, next-door IDs mean nothing about meaning. So the model needs a completely different kind of number for each word. Not one integer, but a whole list of numbers, called a vector. You can picture that vector as coordinates, placing the word somewhere in a space. Watch where similar meanings land. King and queen appear close to each other. Man and woman also land close to each other in their own little cluster. Nobody told the model royalty and gender are related categories. It discovered this purely from reading enormous amounts of text and noticing which words tend to appear in similar situations. And then there's banana, which lands somewhere completely different, off on its own, because it's simply used in different contexts than royalty or gender ever are. Distance in this space isn't random, it's meaning. Now here's where it gets genuinely surprising. Look at the arrow from man to woman. That arrow has a specific direction and a specific length. Let's call that direction gender, just for our own reference. Now take that exact same arrow, same direction, same length, and replay it starting from king instead of man. Watch where it lands, almost exactly on queen. The model captured gender as an actual, reusable direction in this space. A direction it never explicitly learned as a rule. It just fell out of reading text. Our drawing only has 2 dimensions because that's what we can show on a screen. Real models use hundreds, sometimes thousands. We can't picture that directly? But the idea doesn't change at all. More dimensions just means more independent. Directions of meaning available at once. Tense, gender, sentiment, formality, topic, and many more we don't even have names for, all layered into the same point. So embeddings are how the model converts just a number into a point in a giant space where distance and direction both mean something. Everything downstream reasons about words using this space, not the original letters. But there's still a gap. Right now, every word's position is fixed. No matter what sentence it's in, it has the same point whether it means a trophy or a suitcase. Fixing that, letting a word's meaning shift based on its neighbors, is exactly the job of the mechanism we cover next, attention. Read this sentence. The trophy didn't fit in the suitcase because it was too big. What does it refer to? The trophy or the suitcase? Take a second with that. You solved it instantly, without even noticing you were solving anything. But if I only gave you the word it alone with no sentence around it, you'd have no idea what it means. It could point to absolutely anything. And that's exactly the problem the model faces. From Chapter 3, it starts out as just a fixed point in meaning space, a generic placeholder for some object. On its own, that point can't tell you whether it is the trophy or the suitcase. The answer has to come from somewhere else, the other words. So here's the idea attention introduces. For every word, attention asks the exact same question. Out of every other word in this sentence, which ones should I be paying attention to right now? And how much? At first, imagine every other word gets a small, roughly equal share of attention. A totally naive guess. But equal attention to every word clearly can't be right. Didn't tell you almost nothing about what it means. So the model learns to weigh words unevenly. Here, it ends up paying strong attention to trophy and to big, because something being too big to fit is precisely what makes trophy the sensible answer, and weak attention goes to filler words like though or in. Concretely, this comes out as a set of numbers called attention scores, one number per word, all adding up to 1, like a 100% split across the whole sentence. The highest scoring words are the ones that get to contribute the most to updating its meaning. And then something concrete happens. It quite literally mixes a bit of trophy and a bit of big into its own vector, weighted by those scores. After this single step, it isn't a generic, meaningless pronoun anymore. Its internal representation has shifted to specifically mean the trophy, in this particular sentence, on this particular reading. Now here's the part that's easy to miss. This isn't just something it does. Every single word in the sentence does this simultaneously, each one rereading all the others and asking the same question: what here matters to me? Trophy is checking its relationship to fit and suitcase. Big is checking its relationship to it, all at once. That's what lets the model handle ambiguity, like ours, keep track of context across a whole paragraph, and connect words that are far apart from each other. Things a model with no attention mechanism simply cannot do. That mechanism, every word rereading the whole sentence to sharpen its own meaning, based on which other words actually matter to it, is called self-attention, and it is the single most important idea behind every modern large language model. One round of attention already helps a lot, but one round isn't nearly enough to write a whole paragraph, let alone hold a conversation. So, what do we actually do about that? After one pass of attention, it correctly leans toward meaning the trophy. That's real progress, but that's still just one shallow pass of reasoning. Good enough for one pronoun in one sentence, not nearly enough for genuinely complex meaning. So let's define one repeatable unit, a transformer block. It's just 2 steps glued together. Self-attention, which we just covered in full, followed by a small neural network applied to every word individually, which refines whatever attention just mixed together. Now here's the actual idea behind the transformer. Don't stop at one block. Take the output of that first block and feed it straight into a second identical block, and let it do another full round of attention and refinement on top of the first. Then, do it again. And again, a real model stacks dozens of these blocks directly on top of each other, the output of one always becoming the input to the next, each pass adding one more slightly richer layer of understanding on top of everything learned so far. And these layers aren't redundant. They specialize roughly by depth. The earliest blocks, near the bottom of the stack, tend to pick up simple, almost mechanical patterns: grammar, word order, which words usually follow which. The later blocks, near the top, build on all of that groundwork to represent far more abstract things: tone, factual relationships between distant parts of a sentence, even multi-step reasoning chains. Depth is what buys the model the ability to go from grammatically correct to actually make sense. One more detail, and it matters more than it looks. Each block also keeps a direct copy of its input flowing around it, skipping the block entirely. This is called a residual connection. Why bother with a shortcut? Because it means the model can always fall back to. Just pass the information through unchanged, if a given block genuinely has nothing useful to add at that point. Without that safety net, stacking dozens of blocks this deep would be far too unstable to train at all. So a transformer isn't one single clever trick. It's the same clever trick, attention, plus a small refining network, plus a safety shortcut, repeated dozens of times, each layer quietly building on everything the layer below it already figured out. Everything we've covered so far, tokens, embeddings, attention, the whole stack transformer, describes a machine that can process words. But a freshly built one of these knows absolutely nothing. So where does all its actual knowledge come from? Right after it's built, a transformer is just structure. Attention, feed-forward layers, all the machinery we described, but every internal number inside it is random. it hasn't read a single sentence yet. Ask it anything and you'd get gibberish. Training starts by gathering an enormous pile of text, books, articles, websites, code, essentially as much human-written language as can be collected, and giving the model one absurdly simple task to practice on, over and over. That task is given the words so far. Guess the next one. That's it. That's the entire job. Let's watch it. Try on one tiny example. The cat sat on the blank. Early in training, before it's learned anything useful, it might confidently guess dog, and it would be wrong. The real next word in the training text, mat, is right there, and the gap between what it guessed and what was actually correct tells the model exactly how wrong it was. That gap has a name, the loss, and here's the mechanism. The model takes that loss and nudges millions, sometimes billions, of its internal numbers, called weights, a tiny amount each, specifically in the direction that would have made mat more likely and dog less likely. Just from that one nudge, the model is now infinitesimally better at this exact kind of prediction. One example, one tiny correction on its own, that's basically nothing. But it doesn't happen once, it happens again and again, across every sentence in that entire pile of text, billions of times over. Each individual nudge is almost nothing on its own, but billions of them, accumulated, add up to something that can predict language remarkably well. And notice what was never explicitly programmed in. Nobody wrote a grammar rule, or told it what a cat is, or what a mat is. All of that knowledge is a side effect of getting extremely good at one narrow task, predicting the next word, repeated at a scale no human could ever replicate by hand. So that's the entire training loop, start to finish. Predict, measure the mistake, adjust the weights slightly, and repeat, billions of times over, until a machine that started out guessing dog, for the cat sat on the mat, can eventually write in full, coherent paragraphs. Training is finished. The weights are frozen, locked in place for good. So what actually happens the instant you type something and hit enter? Let's follow one real prompt all the way through. The capital of France is... Every step from here on is something we've already covered. We're just going to watch them fire in sequence, back to back. First, your prompt gets tokenized, exactly like Chapter 2. Then, each token becomes an embedding, exactly like Chapter 3. Then, the whole sequence runs upward through every stacked transformer block, each one applying attention and refining meaning, exactly like Chapters 4 and 5. Out the other end comes something specific, a probability for every possible next token ranked here. Paris is the clear favorite at 71%. But look closely, it's not the only option on the list. The model always keeps a full ranked list of possibilities, never just one single hard-coded answer. The model picks a token from that list, usually the top one, and appends it to the text. And then, here's the key part. It runs the entire updated sentence through the whole stack again, from the very bottom, to predict the next token after that. One token at a time, in a loop, predict, append, feed the whole thing back in. Predict again. That's the actual reason long. Replies stream out gradually instead of appearing all at once. The model is rereading everything written so far, from scratch, just to produce each single next word. One setting worth knowing about is temperature. It controls how adventurous that choice is. Low temperature always plays it safe and picks the top prediction every time. Higher temperature occasionally lets a less likely word win instead, which makes the output more varied and creative, at the cost of being slightly less predictable. This keeps going, one word at a time, until the model itself predicts a special stop signal instead of another word, and that's the moment generation ends and control hands back to you. So generation is genuinely just our entire pipeline from this whole video. Tokens, embeddings, attention, the full transformer stack, run once per word in a loop until the model decides there's nothing more to say. Let's walk back through the whole thing, once, start to finish. Tokens turn your text into numbers. Embeddings turn those numbers into points in a space where meaning has distance and direction. Attention lets every word reread the whole sentence and update its own meaning based on what actually matters to it. The transformer stacks that idea dozens of layers deep, with shortcuts so it stays trainable. Training is where all of that structure gets tuned, one tiny correction at a time, across billions of examples. And inference is that same trained structure, run once per word, in a loop, to write the reply you actually read. None of those 6 ideas is complicated on its own. What makes the result feel like magic is doing all 6 together at a scale no person could do by hand. If this made the black box feel a little less like magic and a little more like something you actually understand, drop a like and subscribe for more of these breakdowns. See you in the next one.